natural frequency for this figure. Never mind the scribbles there. So to solve the natural frequency for this figure, we need to find the second order differential equation that describes this figure here. Because from the second order differential equation, recall that if we have this y double prime plus w squared y, and this will be equal to 0. And this w squared is needed to find the natural frequency, where your natural frequency is just equal to w over 2 pi. So, to solve for the second order differential equation that describes this motion, we are going to use the energy conservation. So, we have two types of energy here, the potential energy and the kinetic energy. So, for the potential energy, this is contributed by only two factors, which is the weight W here and the spring here. Whereas for our kinetic energy, it is also contributed by two factors, still the weight W here and the rotational energy that is associated by this two pulley here, which is the bigger pulley and the smaller pulley. Our bigger pulley has a weight, if you can see there, this is for W, whereas our smaller pulley has a weight to W. Now, to start with, we are going to solve the potential energy of the weight that was hanging from the pulley. The potential energy of that one, oh my god, what happened? The potential energy of that one is just given by, recall that the equation for your potential energy is given by mgh. Now, for my case, I assume that the positive direction for y is downward. So, from this figure, the positive direction of my y is downward. So, my equation for my potential energy here, and by the way, your weight is related to your mass by the equation weight equals to mg. So, mg here is just actually the weight of this one, which is just w. So, w times the negative of y. So, y negative of y. Since I assume that the positive direction of y is going downward, so the negative sign here indicates that as my y increases, meaning y goes downward further, my potential energy decreases, which is consistent with the potential energy, since potential energy increases as you go upward or as you travel farther, or as your height increases rather. So, next will be the potential energy that is contributed by my spring. So, the potential energy that is contributed by the spring is given by the integral from the initial length of the spring. I assume that the initial length of my spring, this one, is given by delta to the final length of your spring, or rather instantaneous length of your spring. Now, this delta here, this refers to the length of the spring without the weight being applied, or rather, this is the normal, unstretched state of your spring. So, after the load W, or the weight W is placed on the pulley, is dropped, if you can see here, as the weight is placed here, this pulley will turn, and this weight will travel a distance y, and this distance here is the same y, or the same distance that is stretched by your spring. So from its equilibrium position, the spring will now stretch. If this is delta, the spring will now stretch delta plus the amount of the weight, the amount of the length that is traveled by weight here, which is double y. So the instantaneous length, or stretched of your spring, length that is your spring stretched rather, is just delta plus y. And this will be, the function here is just force times ds. And recall that your force follows the Hooke's law, where your force is just equals to its force, spring constant times its length, or the length that your spring stretched, which is s. So from here, I can rewrite this as delta to delta plus y ks ds. Now integrating this with respect to s, I have 1/2 k s squared evaluated when s is delta to s is equal to delta plus y. So I'll have 1/2 k times delta plus y squared minus delta squared. Simplifying the term here, I'll have 1/2 k times delta squared plus 2 delta y plus y squared minus delta squared, and delta squared will cancel here, and distributing 1/2 k, I will have delta ky plus 1/2 ky squared, and this is the potential energy that is contributed by my spring. And the kinetic energy that is contributed by the weight W is just given by, recall that the formula for your potential kinetic energy rather is given by 1/2 mv squared. Now for this problem, we will only, to make things easier and to cancel things, we will only make use of the variable weight W, your spring constant K, radius R, and theta. So I will discuss what theta is later. So for the also y, your displacement y. Now recall that the derivative of your y is equals to velocity. So I can rewrite this as 1/2 my prime squared. Now since our m is related by weight by this formula, so for the weight that is hanging from the pulley, which is this one, I can just describe this as, in terms of its kinetic energy, as 1/2. Its weight is just W, so its mass is W over G y prime squared. Next will be the kinetic energy that is associated with the rotational energy of your pulley. Now for the pulley that is the bigger pulley, let's denote that as KE2. The kinetic energy of a pulley is given by 1/2 times its inertia times its angular velocity squared. Now if you have angular velocity, if you have a pulley here, angular velocity refers to tangential velocity, meaning the velocity at its tangential part, so v. And also, with this angular velocity, the displacement of this one is theta here. So for the bigger pulley, I can replace its angular velocity as with the derivative of its displacement, similar to the kinetic energy of the weight that was hanging from the pulley. So this, I can rewrite this as 1/2 I times, since your angular velocity is just the derivative of your displacement, which is for the case of pulley is theta, so this is I times theta prime squared. Now to solve for your inertia, recall that the inertia for a disk is just equal to its mass times its radius squared over 2. So the mass of the larger, the weight of the larger pulley is 4W, so its mass is thus 4W over G times R squared over 2. So this is just 2W over G times R squared. Substituting I back here, so I'll have the kinetic energy for my bigger pulley is just 1/2 times 2W over G R squared times my theta squared. Now, to use this theta to cancel my R, recall that if you have a circle, or let's say our pulley here, if this traveled an angle theta, the y, or rather the length here, semi-arc here, let's denote that as y here, if the pulley has radius r, the y here is just given by r times theta. So our theta here is given by y over r. Now, since this is theta prime, we're just going to use the y prime. So theta prime is just equals to y prime over r. Never mind the radius since it is constant. So substituting theta prime with this, I'll have y prime squared over r squared, and then canceling r squared, I'll have also canceling 2, I have w over g times y prime squared. This is the kinetic energy for my bigger pulley. Now, the kinetic energy for my smaller pulley, let's denote that as KE3, still given by the formula 1/2 I angular velocity squared. Now, but unlike for my bigger pulley, I can just substitute the theta prime here, because if you noticed it, since this pulley is smaller compared to the other pulley, then their theta must be different for them to produce the same y here. Now, if you analyze this figure, the length of the semi-arc, which is y this for this case, is just the length of the string that was extended here. So if this this pulley travels certain theta here, so this will also displace a length y here. Now, the amount of length of this string that is released from this pulley is just equal to the y, or rather the length of the spring that is also released by this pulley, since these two pulleys are connected by a rope. So whatever that is released here, whatever the length that is released here, y, must also be the same y that is released by this smaller pulley. So using that concept, I'll have the y, or the length of the rope that is released by my bigger pulley, is just equals to the length of the rope that is released by my smaller pulley. Now, using the same relation, this y is equals to r theta. For my bigger pulley, I'll just have the radius r and the theta. But we are going to solve the theta, or rather the displacement of your smaller pulley, let's denote that as x, that is needed to produce the same y. So we have, but also take note that the radius of this smaller pulley is just 1/2 of the radius of the bigger pulley. So the rs is just equals to r over 2. So I'll have r over 2 times, we need to find its theta, so x. So we can cancel r here since they just correspond to the same radius. So we have x is just equal to theta. So meaning, if your bigger pulley traveled a distance, or traveled a distance rather, theta here, your smaller pulley travels twice the theta here, which is reasonable since this is smaller compared to that one. Kindly use your imagination. So using this value here, we will substitute. For this case, we will have 1/2 I times, remember once again that your angular velocity just corresponds to the derivative of your displacement theta here. So this corresponds to 2 theta prime squared. Now, using the same concept that your inertia is just equal to the mass times your radius, but take note that the radius of your smaller pulley is given by this relation. So this is just r over 2 squared times 1/2, since your r here is still over 2, so times 1/2. And from here, since the mass, since the weight of your smaller pulley is 2w, so its mass is 2w over g times r squared over 4 times 1/2. So 1/2 will cancel here. I'll have w over 4g times r squared. And substituting back my inertia here to this one, I will have the kinetic energy for my smaller pulley to be 1/2 w, wait, this is squared, w over 4g r squared. And by substituting this theta with the value of ry, so take note that for your smaller pulley, to produce the same y, it must turn twice the displacement that your bigger pulley had turned, and also it has a radius that is 1/2 of the bigger pulley. So cancelling 2, I am still left with the same relation of y, which is theta times r. So my theta is equals to y over r, so my theta prime is y prime over r. So substituting it here, I'll have times 4 from here, 2 squared 4, times my theta prime is equals to y prime squared over r squared. Now, canceling r squared, canceling 4, I am left with w over 2g times y prime squared. This is the kinetic energy that is associated with my smaller pulley. Now, using the conservation of energy, where your the sum of your total energy, which is your potential energy, plus your kinetic energy is equal to a constant c. So using all the expressions of potential energy and kinetic energy that we solved earlier, so our potential energy is just negative wy. This is from the potential energy of our weight w plus the potential energy of our spring, which is denoted by delta ky plus 1/2 ky squared, plus the kinetic energy that is associated with our weight w, which is plus 1/2 w over g y prime squared, plus the kinetic energy of the rotation that we solved earlier for the bigger pulley, that was written as w over g y prime squared times the kinetic energy of our smaller pulley, which is given by this expression, plus w over 2g times y prime squared. And this is equal to constant. Now, we are going to derive this. We are going to derive the y here with respect to time. So deriving this, also take note that the derivative of y derivative is not equal to 1, but rather this is still equal to y prime. So getting the derivative of y, we will have negative w y prime plus delta k y prime plus, here, I'm just to get the derivative of y squared. This is just equals to 2y times the derivative of your y, which is y prime. So I will have ky times y prime. Same goes here, plus w over g y prime y double prime, plus 2w over g y prime y double prime, plus w over g y prime y double prime. Now, in case you were wondering where did I get y prime y double prime, still using the same concept that y prime squared, getting the derivative of this is just equals to 2y prime times the derivative of your y prime, which is y double prime. So that's what's happening. Well, that's what's happening here. So this is equal to the derivative of your constant, which is just equal to 0. Now I am going to factor out 1 over y prime. This is because remember that the derivative of your y is equals to velocity, and the second derivative of your displacement is equals to acceleration. Now, for this expression here, if your system is moving, its velocity must not be equal to 0. So I am going to eliminate y prime here, since this is not identically equal to 0. I will let the y as well as the acceleration, which is y double prime, to stay, since this can be identically equal to 0. So factoring out y prime here, I am left with negative w plus delta k plus ky plus w over g y double prime plus 2w over g y double prime plus w over g y double prime, and this is equal to 0. Now combining this term here, I have 4w over g y double prime plus ky is equals to w minus delta k. Now, how to get rid of this delta? Remember that delta, this refers to the length of your spring in equilibrium. So since your spring constant, rather the force of your spring is given by k times s, where s is the length of your spring, or length stretched by your spring, this s this will become K times delta in equilibrium position. Well, delta refers to the length that your spring stretch in equilibrium position, and this is given by force F. Now, for the spring W, the force that it experienced was the weight hanging from the other pulley. So the force is just W, or rather, to solve for your delta, W, which is the force, over K is equals to delta. Now, substituting this back here, I will have this expression to be 0. So, and also expressing this into its standard form, I'll have y double prime plus gk over 4w times y equal to 0. I'm just multiplying the whole thing with g over 4w. And so, from here, I get that my omega squared, to make things less confusing, this will be my omega squared. Omega squared is just equal to kg over 4w. Since, recall that for this problem set, or for the application of linear differential equation, this is just expressed without damping motion. This is just expressed y double prime plus omega squared, rather your w squared y, and this is equal to 0. So, solving for your w, this is equal to the square root of kg over 4w. Now, the formula, your natural frequency is just given by w over your 2 pi. Thus, my natural frequency is just 1 over 2 pi times the square root of my kg over 4w. And I can get this out, so I'll have my natural frequency is just 1 over 4 pi times the square root of kg over w. And this is in hertz. This is my natural frequency.
Closing time. Open all the doors and let you out into the world. Closing time. Turn all of the lights on over every boy and every girl. Closing time. One last call for alcohol, so finish your whiskey or beer. Closing time. You don't have to go home, but you can't stay here. I know who I want to take me home. I know